Okay, let us talk about the IndyCar optimization case. So these are the data inputs. You have 8 potential features that you can add. These are the short-term and long-term cost on each of the features, and short-term and long-term gains, performance gains on each of the features. So first of all, let's put down a list of numbers. These are the decision variables. Okay, this can only be 0 or 1. So let's put down some initial values. You can use all the zeros at this point. We have 8 of them. So these are basically corresponding to x1, x2, all the way to x8. Okay, so these are the decision variables. So we have the cost inputs and we have the performance gain inputs, and with the decision variables, we can easily calculate the objective function as well as the total cost as part of the constraint. So the objective function will be the total gain, okay, which equals to, we can use an Excel function here. So we start with inputting the equal sign. So equal to sum product. Sum product is, let's use the list of short-term gains, comma, the decision 0, 1 variables. By doing this, what the computer Excel will actually calculate by doing 8% times x1 plus 3% times x2 plus 12% times x3 all the way to 5% times x8. Okay, so this is what the sum product function will be doing for you. They're taking these 2 blocks of data, multiply each of the corresponding pairs and sum them up. So this is what we call sum product. So this is for the short-term gain, and of course we can add the long-term gain, which is sum product, or these long-term gains, comma, again, the decision variables. Okay. So this is the total gain. Right now it's 0 because all these decisions are 0. If you are adding a feature, then you can see, the total gain goes up. Adding another feature, the total gain goes up. Okay, so this is how we do the calculation. And then of course we can calculate the total cost, which again equals to sum product, short-term costs, comma, the decision selection, 0, 1 variables, close it up, plus sum product, the long-term gain multiply by the corresponding feature selection variables. Okay, so this is the total cost. This is actually not should not be a percentage. It should be just a regular number. Okay, so if we include a feature, then you can see the total cost will be going up. Including another feature, the total cost is going up again. Including another feature, the total cost is going up again. Including another feature, the total cost is going up again. But this is not doable because we want the total cost to be less than or equal to $85,000. Okay, so this solution is actually not feasible. So let's turn this back to zeros as their initial value. With this model built on Excel, which is identical to the mathematical formulation of the optimization model that we have been written out, it's basically the same as this one. Okay, maximize total gain and subject to total cost less than equal to $85,000, and also all x is a binary. So they can only be 0 or 1, okay? They cannot be 0.5 because you cannot install half a feature. It has to be 0 or 1. Either you have it or not have it. All right, so this is basically how we code the optimization model on Excel. And from here, we can simply let Excel solver to find the answer for us. To include the Excel solver, actually, it's not included in Excel upfront. Somehow Excel, Microsoft decided to hide it. So we need to turn it on. It's actually free, coming with all Excel. This is a Windows version of Excel. So we go to File, and we go to Options. And here we go to Add-ins. And with Excel add-ins, we go to Manage Excel add-ins, click on Go. My computer is a little slow right now. Okay, so we just want to make sure we check mark the solver add-in. We want to make sure we check mark the solver add-in. With that, under data, we will have the solver function included in Excel. Okay, so we simply go to the solver function and they give us a dialog. The dialog asks us a number of things. Okay, let's start from scratch. The objective function, we need to select one cell, which is total gain, and we want to maximize the objective function here. By changing variable cells, these will be our decision variables. So we can select all 8 zeros here. These are the cells, 8 cells. That will be changed by the computers. Of course, they can only be changed to either 0 or 1, but the computer will try all kind of 0-1 combinations and give us the best solution, okay? And then we need to add constraints. The first constraint to add is, of course, the total cost must be less than or equal to 85. Okay, we can just put down 85 here. Or let's close it. We can say this must be less than or equal to 85. We can use this reference cell. So in solver, we can add a constraint saying that the total cost must be less than or equal to this cell. So later we can actually change the value in the cell if needed. We can change the budget, of course, to see what happens. Okay, so this is the constraint. Actually, we do need to add another constraint because if we do not tell the computer that the decisions are 0, 1, the computer actually do not know, and they may give a solution with half a feature, and we do not want it. So we need to add a constraint to tell the computer that all these 8 cells, decision variable cells, must be BIN, binary. Okay, so the computer will know to give us 0, 1 binary solutions. And actually what we're doing here, all the calculations in this optimization model are just linear combinations of either costs or the performance gains. So this is what we call a linear programming formula. All the formulas in this optimization model is linear. So we can use a fast algorithm that's called simplex linear programming algorithm to get the answer. We can use the nonlinear algorithm, but that's not as fast as the linear algorithm. Okay, these are just the algorithm that's pre-coded within Excel solver. And this is all we need to tell the computer. Just click on solve, and the computer says that if you spend a total of $78,000, which is less than 85, which is within our budget, and you can obtain a total gain of 53%, which is the best you can do with this problem. Okay, so in a blink of time, just click on the solve button. You get your best possible solution for your decision problem. And with this total gain, of course, when we are inputting the sum product for the two parts, short-term and long-term gains, we can add weights on the two parts, maybe 0.5 times the long-term gain if you want to discount the long-term gain, but we don't have to do it here. So this is one way to look at this problem. What if we look at this problem from a different angle? What if we want to say that for whatever you do, I want to make sure that I need to obtain at least 0.6 gain. Okay, 60%. At least a 60% gain. What is the minimum cost to achieve a 60% gain? That is a new optimization problem. So basically, the cost constraint can be kind of a soft constraint here. We want to minimize the spending, of course, but we want to make sure that we obtain at least a 60% gain so that we can be competitive. All right. So in order to do this, we can come back to the solver. We can reset everything again, and let us redo all the inputs for this dialog objective function. It will be cost here, and we want to select minimize the cost. Okay, and then decision variable cells still the 801 cells. Okay, we want to add the constraint saying that all these 01 cells must be binary. Okay, and we want to add another constraint saying that the total gain must be greater than or equal to this value. And we'll click solve again. And Excel says that you can actually obtain a 62% performance gain, combined performance gain, if you spend $96,000, which is the best you can do. Okay, this is the minimum money that you need to spend if you want to achieve at least a 60% gain by adding a number of features. So this is how we do optimization using something as simple as Excel solver.